Okay, so hi everyone. So today we have the pleasure to have Alicia Castro from Universite de Bordeaux. So Alicia did a PhD with Timothy Budd in Nijmegen before joining Bordeaux for a postdoc. And today she's going to tell us about quantum gravity and random geometry, and especially JT gravity and Virasoro strings. Please.
Thank you. Thank you for the invitation. I'm very happy to be here, even though maybe Dublin is not very happy right now in general.
I hope you don't have a flight planned for tomorrow.
I did.
Okay.
No, I don't.
No.
Yeah, it was just cancelled. Happy to stay here for one more rainy day. Okay, but today I'm gonna talk to you about well, I repeat myself over and over.
It's already too late.
Oh, this is more or less the title of my PhD thesis was something like quantum spacetime and random geometry, and I keep trying to get random geometry wherever I can in quantum gravity, and I will explain to you how I did this in this very interesting or popular case of JT gravity and Virasoro strings. So this work is based on those two papers that appear there. But let's move forward. So I mean, the first thing that I usually don't do, but in my office, in the visitor's office, I actually found a lot of books. And one of them was a very thin book on just probability theory for physicists. And that actually, yeah, gave me the idea that, well, I mean, we all kind of know what a random variable, a random number is, but how do you actually describe this, okay? And if you don't know it, well, this will be a good reminder. So what a random number is, so one can start thinking about what a random game is, right? So the easiest one is having a cube with the label, with the faces label. So you have labels from 1 to 6, and then you throw these dice, and you record what number you get each time, okay? You do it n times, and of course, when n is very big, what you will have in your notebook or where you have in your recordings will say that, well, each number came out more or less one sixth of the times that you threw the dice, that you repeated this experiment. Now, this is where we kind of incorporated these numbers that are something deterministic, right? It's just integer numbers from 1 to 6. We kind of introduced this randomness there by associating something from the real world, something that we cannot really control, but that has certain probability to come. Okay. So now we can write this in an abstract way and think about this set of numbers 1, 2, 3, 4, 5, 6, and assign a number to each of them, okay? And the number that we assign to each of them is exactly going to be the probability of getting these numbers in this game that we played before, okay? So I'm going to assign a real number, and usually you want these numbers not only to be real, but to be positive, okay? In order for them to have like this interpretation of probabilities. And to this whole bunch of things, which are not only their numbers, but also this number that you assign to them, is what we're going to call a random number, okay? So in this case, we have a set of 6 random numbers with equal probabilities each. This is what we call the uniform probability distribution. And one can actually, well, you can also do a representation of what these probabilities are. So you have here the numbers in the x-axis, and in the y-axis, you're going to have the value of this real number for each of your not random numbers. Okay, so just the integers. And now one can think about like what a random number is, or this set of random numbers, actually not as this list, which would only be integers, but actually as this whole set where you have the numbers, but you actually also have another direction that tells you how likely it is to get them if you thought about it in this way. Okay. So, and here I am showing you like a very simple example where the set of numbers is just 1, 2, 3, 4, 5, 6. But really, I mean, you can generalize this. The easiest way would be to, if you want, choose the interval 1 to 6 and do it in that interval of the real numbers. Okay. Do it for all the real numbers, or do it even for more difficult, complicated. Okay, so that is the easiest example of what a random variable is. So you need not only the variable, which in this case are these numbers, but you also need the probability distribution attached. Okay, so now I will jump very fast to something more complicated, which is quantum gravity and its relation to now another random quantity, but now it's not going to be a number, but it's going to be a geometry. Okay, so let's start by what we think about quantum gravity. So we have some systems, or our whole universe, which are described by some theory of gravity, and we know at least more or less well this theory in this classical regime. We can make predictions. So now, in order to quantize this theory or to understand what's happening with very high energies, then what we usually do, well, you choose your favorite quantization method, you try to quantize the theory. What I am illustrating here is, well, kind of a perturbative approach, okay, where you would consider a space-time and then start considering perturbations around the classical solution and then quantize these perturbations, okay? But in general, you can choose your favorite quantization scheme. And one of these quantization schemes is to perform a path integral, okay? So if I choose, well, you can choose also your favorite action, gravitational action. If I choose the Einstein-Hilbert action, then what I need to do to quantize the system is to perform this path integral, okay? Where my field for these perturbations, in some sense, are going to be just given by the metric. So yeah, so let me now try to understand what this path integral will tell me. So again, this is the metric. Here I have my favorite, well then here I have the Einstein-Hilbert action. And then what you can see here is that, well, the metric is really giving me the information about the geometry of my space-time. And what I could think of is...
Excuse me, are you in a particular dimension?
Not yet. I will go to that. This is just schematic. Yeah, in general, this I will explain in next. So you can think of this path integral of, well, choosing a metric or choosing or integrating over this variable, but you're not integrating over it arbitrarily, but you have some function that weighs, right, how much each of these metrics contribute. Well, that's just the basic idea of the path integral. But in this case, since this field actually qualifies the geometry of space-time, so this is as this idea, this represents a sum over geometries, but with a probability distribution associated to this action. Okay,
so this is not a probability distribution. You're going to go to Euclidean space to get a problem.
Yes, I am going to go to Euclidean. Yes. Yeah, so here I am not doing anything formally. I'm just giving you the idea of where, a rough idea of where the random geometry really arises when one is doing any theory of quantum gravity in principle. Okay, so this is where the notion of a random geometry arises. But of course, as you have already mentioned, this sounds like a very nice idea. We should do that for quantum gravity. But our universe, first, is four-dimensional. And in 4 dimensions, as you know, we have gravitational waves. So the classical equations of motion and just the fluctuations of the metric, and well, here there's also a rich scalar, but it depends on the metric. Even if you integrate over those degrees of freedom, you still have residual degrees of freedom. They are difficult to integrate over, okay? Even if you don't have any matter. We also have a causal structure. That means that this I in the exponential is not, at least not trivial to get rid of it, as we usually do in CFTs, because the causal structure of our spacetime is dynamic, so we cannot do big rotations as trivially as we do in QFT, and there are curvature fluctuations. So in general, our spacetimes, the geometries that we have to sum over can be very wild. So this this whole path integral is not going to be well defined, or is not. I'm not going to be able to give this interpretation to the path integral.
You have a boundary.
Yes, and this is not even with boundaries. So with boundaries, it gets even more difficult.
So you never know.
No, in general, yeah, for 4 dimensions with boundaries.
I'm just wondering whether you are working with boundaries.
Oh, yes, I will be working with boundaries.
So what's the boundary?
Oh, I will tell you. But I will be working. So our universe is very, very difficult. So my favorite dimension to working is 2. Okay, so I will be thinking about surfaces. I will be thinking about Euclidean surfaces, so I'm gonna forget about causality. And you can also do something else. You can also restrict the curvature of your spacetime. Okay, so one of these theories where you do, okay, so here there is a pink circle getting all of these together. Okay. So one of these theories that do a lot of those simplifications that allows you to compute path integrals is JT gravity, where you also introduce boundaries. Okay. So in JT gravity, you have these 2 conditions, and there's also a restriction of the curvature. The restriction is that the curvature is negative and constant. And there's also another model called a newer model for the Virasoro minimal spring. Again, it's 2-dimensional and it's Euclidean, but there you're not restricting the curvature. Okay.
When you say sorry to give you a when you say curvature less than 0, do you mean strictly less than 0 or less than equal to 0?
Less than 0.
Okay, so you don't allow anything flat.
No. And actually, for my case, it's going to be constant, and it's going to be minus. So
okay,
there is no fluctuations of curvature. Okay, so let's start with one of these simplifications of quantum gravity. Okay, that is called JT gravity. So again, this is a model, a 2-dimensional model, where, well, I guess you are physicists, so I'm giving you the action. Okay. This is the action of JT gravity. So as you can see in the first term, we have the Einstein-Hilbert action with boundaries. Okay, so here you have an extrinsic curvature and a metric boundary. As you may know, in 2 dimensions, Einstein-Hilbert's action is topological. So this integrals just reduced to the Euler characteristic of the surface, and that's why it's said that Einstein-Hilbert gravity is topological in 2 dimensions. Okay, so that's the first part. The second part is exactly what characterizes J gravity. Okay, now you can realize that we have the metric both in the bulk. Okay, I'm going to call the surface the bulk and split it between bulk and boundary. Okay, so in the bulk you have the metric in both the bulk and the boundary, the curvature is bulk, but you have this field phi. That field is a scalar field. As you can see, there are no derivatives of that field, so that field kind of is trivial, well, almost trivially sitting there in the action, but it actually has a very important function, and that is that if you compute the equations of motion for phi, they are very easy since it is just linear everywhere. So the equations of motion for phi in the bulk are just r equals minus 2. Okay, reach scalar equals minus. That means that the equations of motion of phi set your geometry, the geometry of the surface, to be a hyperbolic surface. Okay?
Well, what about the value of k?
The value of k, yeah. So k is not going to have restrictions in terms of its value, but instead in terms of how much it can vary. So I'm going to be considering, or well, and people in general in gravity consider surfaces for which the extrinsic curvature is small. That means that the boundary is just a bit wiggly. Yeah, but in general, I mean, that's actually why I put this image here, because if I was not considering, if I was not putting by hand a boundary, okay, this boundary of M, I would be considering a 2-dimensional universe that is just hyperbolic space, okay, and that is this disk that I'm showing you here without the blue line, okay? So this is what it's, well, the Lorentzian version of this is just ADS space.
You haven't really shown us the equations of motion for phi, because if I vary the metric g, I'm going to get a differential equation for phi.
Yes, yes.
Which would be, I would have described that as the equation of motion for phi.
Well, okay, what I'm calling here is the equations of motion. Yeah, what I'm getting from varying the action with respect to phi.
Yeah, I see that, but
yeah. Phi is also going to have, well, phi is going to appear when you take the variations with respect to g. Yes, but these equations are decoupled. Okay, so that is not gonna change the fact that R is set to minus 2.
Well, you also have to worry about the metric on the boundary, little h.
Yes.
You can either have an induced metric for the metric in the interior, or you can have some other.
No, it is the induced metric.
Okay, so that's an assumption. Also, you have to tell us what the value of little k is.
Yes.
That's an input, right?
Yes, I will tell you. Okay.
It's not really a hyperbolic surface, it's a hyperbolic object of some higher genus.
Yes, exactly. Here, I am just showing you
some number of disconnected components in this boundary. I mean, all those things you have to.
Yes, I will. Yes, so here I am showing you the hyperbolic disk, which is the case for, well, which is the genus 0 surface. But in general, I can have hyperbolic surfaces that have higher genus and that have a non-trivial number of boundaries.
I don't think it's genus 0.
The hyperbolic disk? Yes, it is genus 0.
Sphere is genus 0.
Yeah, but the sphere is a surface with positive curvature.
Yeah, sure.
Yes. So, but for a negative curvature, you also have these zero surface.
But there aren't any with genus 0.
Sorry?
I don't think you can have negative curvature of G equals 0.
Yes, you can. Yes. Yeah, so, I mean, you can, in general, consider the space of all possible surfaces. So, you have the moduli space of surfaces or complex curves. And for genus 0, you have the hyperbolic disk, and you have the sphere.
The sphere has Euler characteristic too, which you get by integrating its curvature.
Yes. So I said, genus 0, not Euler characteristics. Yes, I said genus 0, not Euler characteristics.
Yeah, but I'm just saying, if you take the Euler characteristic, and the object that you're considering is a sphere.
Yes.
It has a boundary. You integrate the Euler characteristic, you get 2.
Yes, you will have to.
But that's also a curvature. The curvature is minus 2, minus 4.
Yeah, I mean, but that the sphere is not going to appear in the ensemble of geometries that this action is. Yeah, this action is.
The hyperbolic plane has infinite area, so constant curvature. I think she's right that it would have Euler characteristic 0, the same as the plane.
For which one? For
the hyperbolic disk.
Disk,
Yes, yeah.
Yeah, okay. Now I get what you were asking. Yeah, when you integrate, well, to get an Euler characteristic equals to 0. Yes. So the disk, the hyperbolic disk has genus equals to 0. So has no boundary, at least with this time.
You can't have both ways. You have to have these numbers pinned down. I have to say what the boundary is. Genesis.
Yes. I will tell you in the next slide. Okay. So now that I introduced the action for daily gravity, and give me some slides, and I will continue explaining what the genus and what the boundaries are. Okay. So we can compute partition functions, okay, of these or path integrals if we were not considering. We're in the Euclidean case, by the way. I forgot to mention it again. So we're in Euclidean spacetime, so that's why I'm using partition function as synonym for path integral. So when you compute the partition function, you're going to need to integrate now not only over metrics, okay, but you have this extra field, and the extra field is this scalar field that appears in the daily gravity action. What I am writing here as the betas from 1 to n. So these are going to be these boundaries, okay? One type of boundary, because I will introduce more. One type of boundary that is associated with this term, okay? With this term where you have the extrinsic curvature and you have the induced boundary, okay? And these betas are labeling how long the curves are. And the G that.
What do you mean labeling how long they're?
Well, they are actually a renormalized length of the.
So it's a quantity of the dimensions of length.
Yes.
No.
Yes.
I don't see why you need it, but does it mean you've got n boundary components?
Yes.
So you should have an n there.
Yes. So
no,
here.
No, at the bottom. Your chi has got a little k.
Actually, no.
No.
No. And I want to explain that right now you have to wait. Yes. I will explain why K and N can be that. Okay. But for that, I first need to decompose these surfaces. Okay, so these betas are going to tell you what the length of the boundaries of this manifold are. Okay, and now when you want to integrate, when you want to compute this path integral, if you put this action here and try to do the computation, what you will find is that you can kind of split this partition function into two parts. Okay, so in the bulk you will have this is a constant, so you can really put it here. Okay, so this is, you will have the Euler characteristic coming from Einstein-Hilbert, and then here you have sorry, I didn't say this is called the dilatant field. Okay, the scalar field is called the dilatant field, so I will refer to that. So you have the dilatant field, and the dilatant field acts as a Lagrange multiplier in this action. So then you can actually do the integral over this dilatant field in the bulk, and you're going to obtain, you are going to obtain a delta function that applies this condition in terms of the Lagrange multiplier. And then you're going to get the remaining thing, the integrals that you can do. And here you keep the integral over the dilaton, the scalar field, and you're going to have the boundary.
Why don't you have to integrate over the space of matrix H on the boundary, which are fixed values of beta?
Yes. So I am not writing the expression for G, but since this is the induced metric by G, then and exactly the parametrizations of this wiggly curve.
What wiggly curve?
In the last slide. So what H is, so you have a metric G that is defined in the whole hyperbolic surface, okay? And this boundary, you can think of it as embedding a circle in this hyperbolic surface, very close to this, what's called the asymptotic boundary. And then the metric H is just going to be, well, the metric is the metric G, but together composed with I always forget, this pull back or push forward of the embedding of the circle, a circle without wiggles, to the hyperbolic surface. Okay, so you can parameterize. What I am saying is that this H can be parameterized by G and the embedding of the circle.
You're saying H is fixed by G?
Yes. Not geometrically fixed, but fixed by G.
Just you've set the cosmological constant as your setting dimensions here, so you've set it to 1. But that would have given
what? Sorry.
The -1 for the other term. Why is it -1? Why don't you have a free parameter there?
Yes, this was set by people in string theory it was done this way just to match some quantity.
So you're saying you do have a free parameter there, but you've chosen it. I mean, I would have expected a free parameter there.
Yes, I mean,
If you put it equal to lambda, what would you get?
if you put a lambda here instead of 2 lambda.
If you put a lambda, instead of k minus 1, if you put k minus lambda, what would happen? It doesn't matter, yeah.
Yeah, okay. I have an idea, but I don't know if I am sure of what I'm gonna say. Okay. So yeah, so continuing here, what I want to say is that, well, when one computes a partition function for J gravity, okay, this partition function decomposes into a part that depends on the bulk and a part that has boundary degrees of freedom. And the important thing here is that the bulk part has a genus expansion thanks to this Euler characteristic. Okay, so remember you will have here the Euler characteristic, which is 2 minus 2g minus a number of boundaries. So here you have, okay? And this delta function, what it is doing, even though it looks scary, it is again just restricting the surfaces that you're summing over for your path integral, okay? The surfaces are just telling you that they are going to be hyperbolic surfaces. So this is where it simplifies, when JT gravity simplifies the problem of computing a gravitational path integral, because, well, kind of by hand, of course, we're constructing some action that gives me this simplification in the path integral, and that reduces my problem of imagining all possible surfaces to considering only hyperbolic surfaces. Of course, in the case of 2 dimensions, there are not a lot more surfaces than hyperbolic surfaces, but it's a start. So now I want to show you some examples of, so you see how this topological, genus expansion, okay, works. So here again we have the hyperbolic disk. Now I am not putting the Escher-like images inside, but this is, you should really think this is hyperbolic space, the black circle, and then you have this wiggly boundary, that are the boundaries you're considering JT gravity, or this is the case genus 0, and k equals to 0. So in this case, the path integral, the partition function that I showed you before, can be simplified, and it actually takes the form of Schwarzschild derivative. Okay, you can compute explicitly the whole partition function, and you get some results that I'm presenting you here. Okay, where this beta, remember beta is just the length of the blue boundary. And well, that's called the Schwarzschild partition function. Yep.
You've got a circle there labeled beta.
Yes, it's a blue one. Yes.
You've got a blue curve and you've got a black curve.
Yes.
So what are they?
Yes. So the black curve, you can really think of it as the asymptotic boundary of, like, well, the whole
What is the geometry
boundary.
of this surface? I can't see.
Sorry?
What is the geometry of this surface?
Yeah, the
It has a boundary.
Mm-hmm.
Right.
Yes. Yes, sorry. I can. It's really what I am showing you. So the black curve in the other picture is this this boundary at infinity, this asymptotic boundary, and the blue curve is really this wiggly boundary that I'm putting by hand, if you want. I mean, I am just considering that I want to study my action in a geometry where M is well, where dm is this wiggly, is this blue curve that wiggles just a bit, and is not the boundary of any space, and this M is interior.
I don't know. I mean, you have a surface.
Yes.
It has one boundary component. Okay. In this example.
No, it has no boundary.
John, it's a constant negative curvature surface with a boundary.
Well,
it's a constant negative curvature surface with a boundary.
Yeah. What is it?
It's
also.
You could take the constant negative curvature and go with your scissors and cut it out. It's like a cap. She's mapped it onto the what carry this.
Yes, yes, here, yeah, this is this without the wiggly boundaries, the pointary disk.
Yes, right. So you're taking the pointary disk and you're considering a complex subset.
Yes, yes,
Okay.
where the boundary has to be taken care of or not being very.
Never mind about the wiggles. That's
Okay.
fine. You're taking a boundary which is topologically a circle.
Yes, yes, yes.
So you're just taking a disk.
Yes,
Disk.
yes, I am. Yes, that's what I am doing. Yes, I am drawing the. Yeah, I mean it's true that the what I am considering
Okay,
is
you're taking
this-
the pointary disk and you're taking a finite subset.
Yes,
That's fine.
no, but not any,
No, a particular one.
but a particular one. Yes,
Yeah, that's
but
fine.
I want to
Now
draw.
I understand what you're doing.
Okay. Okay. So again, the black curve that you can see there can be thought as really the boundary of the pointary disk, and the blue line that I'm considering there is really the boundary of the surface I am interested in. Okay, now I'm just drawing the black one for reference because that's how people in ADS CFT do it. Okay, so that was the case for genus 0.
And you wrote down Schwarzian there, so
Yes.
what's happening is that the action on this domain, if I work out what all of it is, including the boundary term, is the Schwarzian.
Yes, yes. And actually, well, what you were just asking me before, like why do you have the -1 there and not another number, is because with the -1, you get exactly that the extrinsic curvature -1 gives you the Schwarzian derivative.
But you could modify it with a different parameter.
Yes.
But you have chosen the parameter, so
-1, so that you only have the Schwarzian derivative. Yes. So then you have also the second easiest example is when you have genus 0, and now you have one of these boundaries. Okay, so now I think now we can think of it as again in terms of pointary disk. Okay, so here I actually have the topology of the disk. Okay, where I am considering just some subset of the pointary disk, which is the interior of the blue curve. But here you should really be thinking about it as a disk. So here is this black boundary, okay? But now I have a hole in this disk, okay? And that is this other black. And what I am considering, my M, my bulk, my surface, is gonna be the interior of this blue line, okay? And the interior of this blue line is gonna be from here to here, okay? So it's gonna, if you project it on a plane, it's gonna look something like a smashed donut, okay? It's gonna be an annuli, where again, the geometry I'm considering is gonna be.
And what's the value of B?
Of B, yes, B is gonna be the length of this other.
So if the trumpet vanishes by B vanishing, you don't appear to get the upper one, which you should.
Okay, you mean, yeah, if you deform this.
If you contract it to 0.
No, you're not gonna get
It's a good function.
You're not gonna get distortion. I mean, these two surfaces are not topologically equivalent. You will have a puncture in the middle if you deform it to be.
Why not? So you're saying when B is equal to 0, it's a puncture disk?
Yes, yes, exactly.
That doesn't appear.
Yes, it appears.
Her expansion still exists there, and she has the Euler characteristic that hasn't changed.
So another thing I could do is, maybe I shouldn't because I'm talking too much, is if I put a little cap on that.
Cap. Yeah. So you do a disk.
Yeah, a little cap on it. What will happen there?
And well, then you will have another partition function.
Well, I should go to this one.
No. No, because that would have the interpretation of, well, you would need to tune it very, very well. You cannot just put any cap.
But you're getting to the topology of a puncture, so I get around that by putting a disk. Now there's no puncture, it's perfectly smooth topology. So if anything funny happens, you have to attribute it to the way you serve it all.
Yes, but you can put, what I am saying is that you can put some kind of cap. You can put a kind of cap, but not any cap. Because think about it from the point of view of this being some bullshit of some string propagating. Then if you put some cap here, that's equivalent of putting some boundary conditions or some dressing in this boundary. And what that means is that depending on the dressing or on the particularities of this cap, then you're going to have a type of brane attached to this.
Surely your diagram is deceptive in that it should have been drawn as a circle in the Poincaré disk and an outer.
Yes.
It's still constant curvature, so.
No, that's okay, that doesn't matter. It's easy
No, but then it tells you exactly what disk you have to put in.
In this case. Yes.
It doesn't really matter. To your topology, there are more stands.
No, but there's more than topology going on.
Yes, it is not a topological, it has a topological expansion, it has a genus expansion, but this model is not topological. Because you still have the, remember that whatever happens in the ball, that's going to affect what the degrees of freedom in the boundary are.
Sure.
And that's what gives you exactly the partition function. The partition function exactly integrates those boundary degrees of freedom. So you're not going to get some Spartian or some action there, but you're going to get something else. Exactly. That's the only place where JT gravity breaks this topological nature of 2D Einstein gravity. Otherwise, it would be, well, almost trivial. It would just be counting surfaces, as Einstein-Hilbert actually gives.
Well, you've made an assumption about the metric on the boundary. That's what
Yes.
No, I don't think so. I mean, I think what she's working with, the diagram is deceptive is the only thing I would say, and that she should have drawn it as a Poincaré disk with a hole in it. Okay, then there's no problem.
Well, yeah, here I draw it this way because I will go to higher genus. And for higher genus, I really can't draw it as well.
It would be whole, it's the Poincaré disk. The real point is that in this case, you can draw the Poincaré, you can center the hole on the
yes, that's true.
In general, if you've got more than one of them, how you center the holes is.
Yes, that's true. And I mean, I am the assumption I am making in the metric of the boundary of the blue boundary is only that, as I said, well, the embedding of the circle into the Poincaré disk or puncture or the whole Poincaré disk is just going to be not very quickly.
It's not going to be very well.
Wiggly.
Yeah, that's okay. I don't mind about that.
Okay.
But I do mind about the topological structure.
Yes, so the topological structure, so again from here, I mean the genus expansion and the topological expansion, that comes from this term. But from the path integral, you still have this term, you still have these degrees of freedom. This is where the Swartian appears. This is where all the non-trivial computations of JT gravity come from. Because you wrote, you explicitly said that you want this blue boundary, this wiggly boundary. This is the spacetimes you want to consider. And there, the extrinsic curvature and the value of the Dirac point are non-trivial. So this theory is not only topological.
Yeah, since you put that slide up again, I still have some worries about your H because, you know, H is, okay, you now say it's the induced metric on the boundary from G.
Yes.
Right. So you should really think of H, because I would like to think of H as H is a function of this thing you've got G to. When you change G to with a different value. So you can't really, in my view, unless you make some assumption about perturbations of H, separate the path interval into two parts. Factually like that.
I mean this.
The second part is a function of G still.
Yes, I mean, well, that's why this is still inside of this integral.
but you've got a second integral. So you live, are you really
Yes, but
doing
this is over the data.
Oh, I see, but then you should have really looked at the d5 with the dg. I see, yeah, okay, it's just the way it runs. That's all right.
She could have done the same thing by just saying she was working with the twice punctured sphere and without specifying things so explicitly, because that's what she's working with.
Yeah, I'm sure she could be.
Now she's forced in that setting, topologically that's what it is. That's what she's dealing with now. The first one was just the once punctured sphere was a Poincaré disk. So that makes it clear that it is the characteristic one. Sorry?
You can get everything from the Poincaré disk.
Yes, but it's the one punctured sphere. So there's just one puncture. The puncture is at infinity.
Yeah, that's right. Poincaré disk is
now she's got a second puncture.
Yeah.
So that will never go away.
No, but that's just infinity. That's okay. It's not compact.
Now her second puncture is at the origin.
Yeah, so
and it gives a disk at the origin and a disk at infinity.
I talk too much. I'm really going to keep silent the rest of the time.
Ah, it's okay. I mean, Sabine told me that we have as much time as we need. But you can also tell me when to start. Okay, so now I showed you the first two, the easiest examples of this geometry or this topological expansion. Okay, I forgot to say. So again, this is called disk. This is called the trumpet. Okay, because in this drawing it looks like a trumpet, and people like that's why I also draw it that way. Okay, but again, we have in general the partition function that I showed you with n boundaries. Okay. There's a genus expansion that is driven by the Euler characteristic. Okay, so that's what I'm writing here. And in general, you can think that, and those are the easiest examples, but I can really have a hyperbolic surface that has, as long as it has n boundaries, okay, a lot of things can happen in things as long as it's hyperbolic. You can have genus bigger than 0, okay. And for hyperbolic surfaces, at least for a good amount of them, it is proven that one can actually decompose these hyperbolic surfaces. Okay? And the way that you decompose hyperbolic surfaces is that you look for geodesic boundaries of this surface, and then you can cut along there.
Just
yes.
to go back to your trumpet, it wasn't the Schwarzian anymore, because Schwarzian is defined at one circle. So what was it that gave this?
Yeah, so again, you can write extrinsic curvature and you're going to get just something more complicated than Schwarzian, but it is still, you can compute the integral.
It doesn't have a relatively simple form. Like the Schwarzian.
Well, it doesn't have a name at least. It has a simple form because the integral could be done. And this is why I wanted to show you what a trumpet is, and why I wanted to draw it that way. Because when you go to higher genus, okay, into more complicated hyperbolic surfaces, you can actually decompose these surfaces in some part that's trumpets, okay, which are the ones that contain these boundaries that I'm considering, okay, these weakly boundaries. And the other part that you get is that you get a hyperbolic surface now with genus G, okay, so it's kind of like you put all of the holes inside of this component. Well, all of the holes of all of the genus contributions, and you have, in this case, n geodesic boundaries. And these n geodesic boundaries are the boundaries, well, the number that actually appears in the Euler characteristic. And why I said before that n is not equal to k. Small n, some Euler characteristic.
I'm forbidden from speaking.
Okay, it will appear again, so you will see it again. Okay, so the key point here is that these hyperbolic surfaces, the ones that we consider in JT gravity, they can always be decomposed. We choose them such that they can always be decomposed into trumpets plus a hyperbolic surface of genus G and boundaries. Okay, and you can recover again now your partition function for B weakly boundaries by just choosing your taking n trumpets, okay, with the right lengths, and then gluing all of the possible hyperbolic surfaces with n geodesic boundaries that you can include. This is why two-dimensional quantum gravity is also very nice, because I mean, this is exactly kind of the idea of string theory, right? I mean that an amplitude or a partition function, it's actually geometrically, okay? It's like taking Feynman diagrams and blowing them, right? And making them fat, okay? So your particles or these lengths beta, if you want to compute an amplitude that has all of these William boundaries, you actually have to sum over all possible surfaces that fill up the space here in the middle. Okay, so again, another example of why JT gravity is very popular, because you can do this decomposition of the spacetimes that you're considering. And in this case, we're thinking about an actual theory of gravity, okay? Now the analytical way of saying what I just said with this drawing is this one, okay? So your path integral, your partition function can be computed in this way, where you're gonna have some mini partition or partition function blocks coming from the trumpets, from the n trumpets, and you're gonna have a factor, okay? One number there, one function of the length of these geodesic boundaries that I will denote by B. And these numbers or these functions are going to count how many hyperbolic surfaces you have here in the middle. Hyperbolic surfaces of genus G and number of boundaries. Okay, and you have to integrate over all possible lengths, intermediate lengths. Now, these numbers, these B's, these functions of little b, these are the very famous Weil-Petersen volumes, okay? So Weil-Petersen volumes are just some polynomials, actually, in these, that count the number of hyperbolic surfaces of genus G and n marked geodesic boundaries. And these are the ones that, well, were famously also studied by Virasoro, okay? So your partition function, the problem of computing a partition function of quantum gravity, 2 dimensions, hyperbolic space, okay, and Euclidean, became a problem of actually counting the number of hyperbolic surfaces that you can have.
So
yes?
That sounds like a topological quantity.
This one, well, it is. Yeah, it is topological up to the length of the geodesic boundaries. And
so it's a Weil-Petersen volume. And is there any easy way of seeing why it is the Weil-Petersen volume from the path integral?
I mean, you can compute these partition functions for different number of betas. And you can actually check, so these seed trumpets, these partition functions of the trumpet actually correspond to taking some Laplace transform, if you see the form. So they Laplace transform these Weil-Petersen volumes. So you can check that if you compute, the way that people did it is that they computed the partition functions. I
should be able to compute that directly. Because it is given by a particular path integral that you've written.
Yes.
JT gravity, which now with these boundaries. you have the uniformization so that you can put it on the constant negative curvature on the Poincaré disk. So it's some domain on the Poincaré disk with those circles.
Yes, I don't know. I mean, I don't know if it has been done exactly like this, but I mean, in a sense, it's very similar to Beaton's conjecture, to just write a generating function of both theories, because the non-trivial part of JT gravity, what makes it non-topological, is the Wigly boundary.
Yeah, no, that's
when
fine.
you're calling, yeah,
The one reason I'm calling it that it should be, I shouldn't need to do anything other than, well, I can see that it's a volume on the Poincaré disk, and since it's constant negative curvature, I will have it will have these boundary disks, which have to be, well, they have geodesics, you told me, on the
yes.
geodesics on the Poincaré disk. But the geodesics all go to the boundary.
Yes, this is, yeah, I mean, this is non-trivial, at least for me to see in the from a Poincaré disk point of view, because this decomposition.
Yeah.
I am not sure if it has been. Okay, so our old problem, you can tell me when to stop because I think it has been 1 hour. Our old problem of computing a partition function at integral for quantum gravity, okay, now that I assume that I am working within this framework, became problem of working with these numbers, with these biometers of volumes, okay, which count the number of hyperbolic surfaces. Now, even if I don't arrive to what I have done actually, but there was this very famous paper in 2019, the triple S paper, Stott, Schenker, and Stanford, which was named just JT gravity as a matrix integral. Okay, well, I'm gonna, maybe you have always wondered what that paper is about and why people talk about it. I will tell you now. Okay, so we have the biometers and volumes. This is what is here, and they satisfy something called topological recursion. Topological recursion, this is just an image. I've gotten a lot of heated comments for this, this expression, okay? This is just an image. What it tells is that if you want information about genus G, you can compute that information from lower genus quantities, okay? So that's topological recursion. So then if you have a quantity that satisfies topological recursion, it's enough to have genus 0 information, then you can compute higher genus from that initially. It's like an initial value problem, okay? So the biometers and volumes satisfy topological recursion. And another system, another mathematical system that satisfies topological recursion, and I'm not gonna explain why, is random matrix, okay? And now I want to tell you just quickly what you should think about these random matrix models, okay? So a random matrix model, again, it is given, you can think of it as a partition function, okay? Where your field is not going to be some scalar field or symmetric, but it's actually just a random n by n matrix, okay? And your matrices are distributed with a probability distribution given by some exponential of some, we call this a potential, okay? So just, it could be some polynomial of the random matrix. And in this case, I am showing you the partition function, so that means that, well, what you're multiplying here is this trace, this kernel partition function, okay? So it is a quantum system, if you want, where your field or where your physical quantity just turns out to be a random n by matrix. So you can, one of these, well, you can think of one of these. This could be a Hamiltonian, for example, the random variable, okay? So, and this is what is known in the literature as the holographic Hamiltonian of some systems. I'm not going to touch more on that. I just want to say that that this is where the relation between JT gravity and matrix models comes from, is topological recursion. You can map it to the topological recursion of matrix models. And actually, you can think of some very easy distribution for your random matrix that is just going to be a Gaussian distribution. Okay?
Just say very bluntly, you've got V there, and you've got V bar.
Yes, this should be a bar too. Yes, I just realized today that's why I put a bar, but I forgot to put it here. Yes, so for JT gravity or for matrix and volumes, one can actually write a matrix model of this form. There's a bar here, okay? And the only part where the structure of JT gravity or of the matrix volume center is exactly in this polynomial, okay, or in this potential. And for the bimeters and volumes, you will have a potential that is a general, much more complicated generalization of just quadratic equation. Okay. So the reason why I want to say this is because I will use, or at least I was planning to use some techniques of matrix models that I will just take from the pockets of somewhere. Okay, I will just take out and just show you what happened. So let me mention these for sure, and then you can stop me or you can ask me more if you want. Okay, so I promised you that I was going to show you some relation between JT gravity, between some theories of quantum gravity and some random geometry, right? So now we have JT gravity almost as a random geometry, right? I already showed you that in pictures, I can actually compute some partition functions of JT gravity as actually counting the number of hyperbolic surfaces that I need to construct these manifolds. But there is something that I still need to compute to prove to you that that is actually a theory of random geometry. Okay, remember that to have a random variable, you don't need only the variables, but you need a probability measure on them. Okay, so you need your numbers and you also need the probability distribution of those numbers in order to have a random variable. So now I'm just going to show you how to construct the probability measure associated to these hyperbolic surfaces in order to define JT gravity as a random geometry. Okay. Now this is where I'm going to take some tools from matrix models. Okay, that I kind of justified already why I do that. So I'm going to use something called generating functions. Okay, so here I just have my bimeters and volumes. These are number of hyperbolic surfaces. Okay, these are just polynomials. I'm going to put them in some very complicated expression, such that if I take derivatives of this expression with respect to mu, and I set mu to 0, I will get the numbers. Okay, that's a generating function. This is very useful to use because a transform of the generating function called x, called the string equation, actually has a power. Well, this one also has power expansion, but this power expansion is easier to see. These are the Bessel functions, Bessel function of first kind, I think, and this one third kind. Okay. These are just Bessel functions, and you can think of it expressed in a power series. Okay. So this is the string equation, which you should be thinking of it as just a generating function of bimeters and volumes. Okay. Again, take derivatives with respect to mu, set mu to 0, you will get the bimeters and volumes. It's just a transformation.
Sorry, how do I read this? F0 of mu1? It's not clear to me how to read this.
F0 of mu.
it should be a functional of mu because mu was some functional.
Yes, it is a function. These are functionals, yes.
So you've got an integral from 0 to e of mu of some relatively simple function.
Yes, you have an integral from E0 to E.
So to differentiate with respect to mu, I just need e of mu.
No, because here there is also mu.
That's not so okay.
Yeah, so here this x squared is this expression. You have mu here, but you're right. I mean, you will have to take the derivatives with respect to this mu, and you also have to take the derivatives.
So it's a functional derivative with respect to mu that you're supposed to take here.
Yes, yes.
It looks very formal. So.
What is E mu?
Yes. Okay. So E mu in the mathematics literature is just called the solution to the string equation, and this gives you just some radius of convergence of your formal series. Okay. So these are formal power series. This is just a radius of convergence. In JT gravity, well, in physics, when you study matrix models as some random Hamiltonian, in a random Hamiltonian way, this in mu, actually it's negative, it's called the ground energy of the holographic quantum system. Okay, so this has a physical meaning well, for JT gravity or for the holographic system. Okay, so just going to be the ground energy. Yes.
So is that some solution to the Virasoro constraints? Is that where that comes from? Or?
Yeah. I mean the F0 is practically just the KBB tau function. So yeah, so higher genus, the higher genus ones should be well, our solutions to Virasoro.
But as in the J of the string equated x of like the answer is a Bessel function. Is it a
which one? This?
No, the bit below it.
This one.
Yeah.
Yes. So this string equation, the version that I'm showing you, is the solution to the genus 0. Well, I call the Helpandiki equations, which I think are genus 0 versions of, well, they are equivalent to Virasoro constraints. I don't remember if they are exactly the same equations, so you have to do some extra steps. But yes, I mean I am just writing topological recursion in other variables. In these variables of the string equation in particular. Okay, because the string equation is very much used in this literature. And yeah, this is particularly the tool that Clifford Johnson and myself have been using to study it. Yeah.
I know I said it this week. Just asking, the I0 there, what is that?
Bessel function.
Oh, sometimes they use K, but they're using I and J. Okay.
Yes.
I is one of them as well, Brian Charles.
Yeah, I know you can use K and J
well,
on a basis, but that's all right. Fine.
Yes, these are the ones that I choose to use. Okay, so I am using these tools coming from matrix model or from topological recursion, as we see there are synonyms. Okay, from topological recursion, in order to write my topological recursion in terms of this generating function in this string equation. And now what I can do from here is that if I have remember that the bifitters of volumes are inside the generating function. Okay, these are going to be the ones that count how many hyperbolic surfaces I have. Okay, so if I want to sample surface, okay, with some probability, then what I have to do is that if I wanted to sample uniformly, that means just take 1 over the number of total, the total number of options that I have. I could do 1 over the the number of volumes, which I packed in generating function, okay? But in order to write this, well, to make this consistent and make this actually a probability distribution, okay, I have to multiply by this dummy variable, the one that I introduced in order to write the generating function. What I am showing you here is a well-defined probability measure in the space of hyperbolic surfaces, which, if you believe me that this is a good probability measure, lets you write JT gravity or makes you understand why JT gravity is actually a theory of random geometry. In the sense that you have some geometries, you understand the geometries, and you understand what's there. You can write a good probability measure with this geometry. So now you have your per geometries, probability distribution, you have a random variable, you have a random geometry. Okay? This was a step still to be done. So at least I put my name there somewhere, okay? So this was a step still to be done. As you can see, all the ingredients were there, the ideas were there, the pictures were there, but one actually needed to go one step further and use this language of generating functions and string equations in order to write this in a well-defined manner.
So Alicia, you're saying that if I look at the bottom of the slide, then to go to the top was the bit that you were working on. Is that what you're saying?
That I have to what? Right?
Your hand is there, right? So
Yeah.
if I start there and I go to the top, that's what you did, is it? What were you saying?
Yes. Yes. Well, what?
Just trying to understand. So that's a recent, because that's 2023.
Yes.
Okay, very good.
Yes. Well, just one thing more, okay? Because I introduced this dummy variable, if you want, this mu, that serves just, to take these functional derivatives to make this generating function about liters and volumes. But actually, the way that you can interpret them, again, and that's why this was not just some trivial mathematics work, is because these mu's actually have a physical meaning. The physical meaning of these mu's are, in these hyperbolic surfaces, some geodesic boundaries where I didn't glue a truncate. Okay? So remember, I can split my JT gravity path integral into a part that can have genus and can have a lot of things, and then this part, the trumpet, that contains the Willy boundary. Okay? And what I was doing before is that to each geodesic boundary, I was attaching a trumpet. Okay? That would give me an endpoint partition function. Well, endpoint function. Now what these mu's do when you introduce them is that they actually give you some degrees of freedom. They allow you to choose not to glue a trumpet to all of the geodesic boundaries. And what this means geometrically is you will have some geodesic boundaries which will be intrinsically defined by some function mu of L, which is the length, the geodesic length. Okay, and the way in which string theory speaks about this construction is actually thinking that this mu is actually just a representation of a boundary, of some physical boundary being there, and these are called branes. Okay, so introducing these mu's, which is what allowed us to write a probability distribution, which is needed to write a probability distribution, actually introduces in the quantum gravity theory some brane systems. And you can even check, I mean, of course we have to check this, that it makes sense with the literature. In these two papers, people explore JT gravity coupled to two kinds of branes, FCCT branes and end-of-the-form branes. Okay, these are just names, different boundary conditions, or these boundaries, these geodesic boundaries, not the big ones, they are different. And they computed the partition function, okay, objective gravity of these branes and more quantities. And what we checked is that these systems, these very physical systems with some branes, are equivalent actually to choosing these mu's, okay? These what we thought were dummy variables, these functions in the generating function as these two functions of the length.
Can you just say that again?
Yeah.
Can you just say this couple of sentences again?
Yes. So what we showed is that you get the same partition function, the same results for the partition function, if you choose these mu's as these two cases.
Are you saying those two cases are the same?
No, they are not the same. No. What I am saying is that there is an actual correspondence between putting the weight.
That's what you were saying. The same.
Yeah, no, they are not the same. No, they are not the same. Yeah, but there is an actual correspondence, proven correspondence between these functions mu in the generating function and branes at the partition function level. Okay. And okay, that's all I'm gonna say.
What does FZZT stand for?
Names. One of these is Salmodovich, the other ones I'm sorry, but I don't remember. Okay, and this is all I will say for now. Yeah, I have more geometry results, also Virasoro strings, that is something that has to do with CFTs. So if anyone is interested, I also have something on black holes. So yeah, even if you don't want to ask now, you can ask me later.
Sorry for asking too many things.
Don't worry, it was great.
But it's my only chance if I'm in the same room with the person. I was just intrigued, it's more a historical point, but on the previous slide, you had that net surname, is it Marakazi, this Iranian woman?
Virasoro, yes.
Who died young, she got a field spell.
Yes.
Was that an interesting reference? Can you comment on that?
Yeah, I mean, no, she actually wrote very, very well. Yes. Mirzakhani's papers are very well written.
But nice. Can you say, do you know anything about that one?
I mean, well, this one is the most famous.
Okay. So what journal is it in?
It's in communications of mathematics.
Okay.
Yes. Yeah. But also if you Google random geometry and random hyperbolic geometry, you will find.
Yeah, and also Ed Witten wrote kind of expository article about your work after she died.
Yes, and he's one of the people that always, when he mentions her in a talk, he always mentions that she was a woman.
Oh,
yeah.
I think everybody knows that. But the important thing is she got a field spell.
Yes. Yeah.
Can you show us the next page? I mean, this definition of the partition function by matrix model is very straightforward. Was it no, just continue? It was the more complicated one.
Okay. Yeah.
So how is this related to your matrix model again now?
Yes. So when you have a matrix model, so I wrote the matrix as H.
Yes.
Okay. So what your variable u is here will be H.
It's presumably the eigenvalues of H.
Yes, you can. Yes, exactly. So you can diagonalize the random matrix, and then you will have n random eigenvalues.
You're taking into infinity, presumably.
Yes, this is double scaling limit. So yeah, I am using already a double scaled.
So what is your double? N is going to infinity
and some coupling is going to. Well, in this case, the coupling that is going to go to a critical value is going to be.
Another thing is that the J1 is entire in the square root of u, but I0 is not.
Yes, exactly. Yes. That is yeah, that is important also.
So I still haven't got the full connection with the matrix model.
Yes.
These V of G and H.
Yes. So okay, so you start with your matrix models that hasn't been double scaled, so it hasn't been taken to infinity. Then what you can do is that you can, as you said, you can diagonalize your, well, you can go to eigenvalues.
Yes, and I can just pick the Gaussian matrix model?
No.
I can't.
For JT gravity, you cannot. It's gonna be something much more complicated. But you can do this exactly, you can construct these two, I mean, which you're not gonna get parameters and volumes or something else, for the quadratic, for the Gaussian matrix model.
So how are V, G, and K related to the matrix model?
Yes. So for the Gaussian case, what you're gonna get is XU equals to -2. So there's gonna be, you can see this is a power expansion. So you're gonna have a lot of terms that just.
You've got a potential for your matrix model.
Yes.
That's the only thing that's complicated in there. So how, and I can get the eigenvalue density from that potential.
Yes, from that potential, yeah.
So we can, we're going to get some steepest descent equation for the density. Yeah? How is that related to this system?
Okay, yes,
and also that Pearson factors in the denominator, which is a bit peculiar.
In the denominator where?
Probability.
In the probability measure?
Yeah. WP stands for Pearson.
Yeah, but that's the partition function of that system. I mean, we need to go back to get how the definition of F.
Yes.
But then the VGs.
Oh, sorry. Yeah.
It's probably the previous.
See, they're in that. Well,
yes, this one here now. Now, how is this line? I would need to understand how this is coming from the matrix model.
Yes, and from the density of states, right?
Density,
yeah.
Right.
So I can show you. It's just that it is up here. Oops. So this text, this is the string equation.
So this is the eigenvalue density
of the matrix model. Yes.
Yeah. Fine.
Yes.
And this is presumably looks like it's probably the Gaussian case.
No. This is in general. When you're in the Gaussian case, when you're in the Gaussian case, then x is equal to u minus u.
Okay.
So it is just this is just 1.
And how is x related to the potential?
So it is related to the potential in this way. So here I wrote it. Okay. So this is the string equation the way that I wrote it with the Bessel functions. But as I said, you can write as power expansion. Okay. Yeah. These coefficients that appear in front of your powers of u, those are the ones that you can use to construct your potential. So in the case of a Gaussian potential, you're going to have the only contributions from k equals to 1, okay? Because I'm in even powers, so with even potentials. So for the case of the Gaussian potential, you only need k, the coefficient of k equals 1 different from 0, and all the others equal to 0. For minimal models, when you have to start adding more terms to your polynomial, to your potential, then you're going to start making other k's different from 0. And for JT gravity, so the reason why it is more difficult than the Gaussian case is because you actually need all of them.
Yes, but now how is the potential related to these ones? If I just wrote the potential,
you can write.
Is it a sum over from k equals 0 to infinity of tk?
Yes, so they are going to be in the same universality class when you take a double scaling limit.
I just want to. So is it the tk's that define the coefficients of the potential?
Yes. Exactly.
So the potential is sum from k equals 0 to infinity of tk.
Not only tk, also gamma k. I mean the tk plus gamma k. So you can look at it, the TKs are the ones that have these mu's. So they are going to be
those will come in later, but I just want to understand how the direct relationship to the potential.
Yeah. So let's forget.
Can you just write me on the board or something what potential is in terms of those variables?
So you will have H.
Yes.
Yeah, that's how I'm calling the matrix. So you can construct your potential. Oh, sorry. We can put TK equals to 0. So no defects, no branes, just hyperbolic surfaces.
Oh, what did you do?
Well, you can also not make it 0. But you can construct your potential in this way.
So that's going to be your potential.
Yes.
Okay.
Okay.
Starting place this year.
Yes.
And now you have introduced the auxiliary variables mu and as being related to these.
Right. Yeah. So
Supposing I take the TK to be 0, I expected the TK are perturbations of the potential.
I mean, you can also. So
because you've got special values for gamma k.
Yes. Yes. So gamma k's are very important. So these are really KDB times.
These are critical values or something like that of the.
Yeah. Exactly.
Where the eigenvalues are spilling out of the potential. Because you will get critical values if you take a potential, an arbitrary potential, which has a well, and it has some deeper well, or it's unstable potential. Probably that's what you're dealing with. As you fill it to the critical value, you will get a nice scaling limit. That's presumably the double scaling limit you're talking about. And the eigenvalues are spilling out of that at critical values, and those are presumably your gamma k's.
Yes, but I mean, where that happens is when you haven't double scaled, you haven't double scaled the matrix model yet. So that's when you can actually, because when you double scale, you really are going to see just the edge of the distribution, right? So what I am showing you here, this is the potential for the double scaled matrix model. So you know what's happening to the eigenvalues very close to that edge, but you don't really know exactly like how it looks globally, like for the full matrix model.
Yes, no, that's fine. Yeah, I mean,
and just a kind of a language question: why do you write the word times?
Oh, because they again from topological. Well, it's not even. I mean, it's from topological recursion. So there is the bimeters of volumes. They satisfy. They are also in some hierarchy, KDB, the KDB hierarchy, and these are the KDB times. These values are the KDB times, or yeah, for these kappa and tau intersection numbers. So that's why I'm calling them times.
That's what
yeah.
Thank you, Alicia, again.
Please go ahead. Yeah. Thank you. And we keep it especially cold to keep the speaker on their toes.